everyone, so this is the second video in the series 15 Days of Leetcode. In this series we'll be solving all the 75 questions in this list of questions from Leetcode, and in every video I'll solve 5 questions, so I'll create 15 such videos, and if you watch one video every day you can complete this list in 15 days. And today we are going to solve question number 6 to 10. So let's jump right into this. So we are given the head of a linked list and we have to remove the nth node from the end of the list and return its head. And the follow-up is, can you do this in one pass? So for example, here is the linked list 1, 2, 3, 4, 5, and if n is equal to 2, we have to remove the second last node from the list, and we have to return this list 1, 2, 3, 5. One easy solution is to first traverse through the linked list and count how many total nodes are there in the linked list, and nth node from the end of the linked list would be, let's say there are t number of total nodes, would be t minus nth node from the starting of the list. So basically we know that if it's second node from the end and we have 5 nodes, so which means t minus 2, 5 minus 2 is 3, there are 3 nodes before this, so we know that this would be 4th node from the beginning, and we can make that calculation and then we can remove the 4th node from the beginning. And problem is this would take 2 passes, and follow-up question the interviewer is asking that could you do this in just a single pass. So to do this in a single pass we can use 2 pointers, fast pointer and a slow pointer, or first pointer or second pointer, whatever you want to call them. So basically we'll try to keep the distance between 2 pointers equal to n plus 1, and the reason is that imagine that in this case we have a pointer here which is pointing to the null. Imagine an imaginary null node after 5, and then there is a pointer which is exactly at a gap of 3 behind this pointer that would be pointing at 1, 2, 3 hops back, that would be pointing at node 3. So if that pointer is pointing at node 3, then we know that the node next to node 3 is the node which we have to remove, because we have to remove nth node from the last. So nth node from the last means 1, 2, second node from the last is the node which we have to remove, which means we have to have a pointer which is at a position of n plus 1th node from the last, which is like n plus 1th from the null. So we'll have our second pointer here. So we'll take 2 pointers, we'll increase the distance of one of the pointers by n plus 1 units, and then we'll keep moving those pointers one by one until one of them goes and points to null, and then we know that the other pointer is the pointer which is pointing, whose next element is the element which we want to delete, and we will just delete the next element corresponding to this pointer. So let's quickly see this in the code. So list node is the struct that they are using. So I'll just create 2 pointers. List node star first, list node star second. So just create 2 pointers, and we are given n to be between 1 and size, where size can be up to 30. So at least there will be one element in the linked list, it is provided to us. And to handle the case where there is only one element, in this case we'd want a gap of 2 between our 2 pointers according to our algorithm, but we can't have a gap of 2 if we start our both first and second pointers from the first element in the linked list, because the next element is a null and you can't have any more elements, so we can't have a gap of 2. And that's why to handle such cases what we'll do is we'll add a dummy node in front of the linked list so that we can have at least a gap of 2 if required. So let's create a dummy node. and we'll use this constructor which will assign the value to this node. We can assign any value to this node, it doesn't matter. Let me assign -1. So dummy nodes next pointer would point to the given head, and our first and second pointers would be initialized to dummy node. Now we have to maintain a gap of n+1 between our first and second pointers. So I'll increase the second pointer n+1 times. So this will loop will run n+1 times. So second is equal to second next, and once I have done that, I'll wait till second becomes null. While second not equals to null, I'll increase first, I'll increase second. So after that we keep on increasing both the pointers simultaneously, and once second becomes null, we know that the pointer right in front of the first pointer, the node right in front of the first pointer, is the node which we want to delete. So we'll say first next is equal to first next, and we'll simply return head of the list. So head of the list would be dummy node dot next. So let's quickly try to run this code. So this code is accepted. Let's try to submit this. Yes, the code has been accepted. So this was a pretty straightforward question. You just need to know the trick of having two pointers to keep track of the distance from the end. So let's jump right into the next question. So it's an easy question. Given a string s which is containing just the characters opening bracket or a closing bracket of different forms, determine if the input string is valid. And an input string is valid if opening brackets must be closed by the same type of closing brackets, and opening brackets must be closed in the correct order. So for example, this is valid, but this is not valid because there are different kind of opening and closing brackets. And also this is not valid because we have an open bracket of one kind, but we haven't closed this bracket, and because we have opened a bracket of one kind and then we again open a bracket of another kind, and then we should have closed the bracket of kind 2 here first before closing the bracket of the first kind. We can use a stack for this. So what we do, we will only push opening brackets in the stack, and whenever we encounter a closing bracket, we will not push that into the stack. In fact, we'll check which is the topmost element of the stack, and if the topmost opening bracket in the stack matches that closing element, it means that we still have the valid structure. Otherwise, if it does not matches it means we do not have a valid structure. For example, in this case, we'll have a circular opening bracket and a square opening bracket, and then we push both of these to the stack, and then we encounter a circular closing bracket, but then we check the top element in the stack, which is a rectangular opening bracket. So this is not a valid expression. So let's quickly see how we can implement this in the code. So we'll have a stack of characters, and let's create a function which checks if it is an opening bracket. C should be equals to either this, or C should be equals to either this, or C should be equal to either this. So if in either of these cases we return true, else we return false. So if is opening, if current character is opening, we just push it into the stack. Else we check stack's top element is complementary. Stack's top element is complementing the current element of the string. If that's true, if that's false, we simply return false. And complementary means that they are the valid opening and closing pairs. So bool is complementary, let's say character A, character B, both of them are complementary. A and B are complementary if A equals to this and B equals to this. So since we are passing the stack element first, it will definitely be an opening bracket. So we can consider A to be an opening bracket and B to be a closing bracket. So if this is the case, then we can return true, because yes, they are compatible. Similarly, we create other two cases. So if this is the case, we return true. If this is the case, we return true. Otherwise we return false. So if these are not complementary, we simply return false. Else what we'll do, if they are complementary, we can just remove the top element from the stack, because its job is done. And we keep doing it, and in the end we just have to check if stack is empty. If stack is empty, we'll return true, else we'll return false. So return stack.empty, true, else we return false. Because if stack is not empty, means there is an opening bracket for which we could not find any closing bracket, and therefore it's not a perfect match. So let's quickly run the code. So this is accepted. Let's try to submit this. Last executed input is this deadly signal. Let's see. So I think what happens is, since we do not have any element in the stack at this point of time, which means we have more closing brackets than the opening brackets. So if stack becomes empty and we have encountered a closing bracket, we'll return false. So let's try this test case first before submitting. Yeah, it's accepted. So one of the cases we missed out and our code has been accepted. Yeah, so we missed out this case when stack becomes empty, which means we no longer have opening brackets, but we are still getting closing brackets. So that's the case when we have to return false. So if we try to call stack.top on an empty stack, it was giving us the error which we just saw. So let's move to the next question. So it's again easy. What it says is we have to merge two sorted linked lists and return it as a sorted list. The list should be made by splicing together the nodes of the first two lists. So first node of this list, then these two lists, then 3, then 4, then 4. Number of nodes in both lists is in range 0 to 50, so list can be empty as well. The value in those nodes can be from -100 to 100, and we are given that both L1 and L2 are sorted in non-decreasing order, and we have to return a sorted list such that the final list is also in increasing order. Yeah, so this should be pretty straightforward, does not require too much application or does not require too much explanation. If L1 is null, simply return L2. Similarly, if L2 is null, we return L1. Else what we do, we can write this in form of recursion, that we can compare L1 dot val is less than equal to L2 dot val, which means L1 dot val dot next is equal to merge two lists L1 dot val dot next L2, sorry, L1 next slash L2. So basically, if L1's value is less than L2's value, we'll pick this node, we'll point this to node to whatever the merge function would return for merging the next node of this node with the L2's current head. So we do that, and after doing that, so basically assuming we have merged this, we'll return this node. So we return L1, and similarly we can copy this, otherwise we have to set L2's next by merging it with L1, and we can return L2 in this case. So let's quickly learn this code. Shit, man. So there should be no val here, my bad. This has been accepted. Let's see. Yep, the solution has been accepted. So recursive solution for this is very straightforward. Now let's think about the iterative solution, and here is a quick iterative solution. So for the iterative solution, we'll have to have a dummy node. I create a dummy node and attach it to the head of the linked list. So let's say P is the dummy node, and if L1 value is less than L2's value, I'll say that P's next is L1, and P is always pointing to the last node in the linked list. So I increase P by P's next, and I increase L1. And similarly, if L2's value is shorter than L1, then P's next is L2. I increase P so that it's still pointing to the last element, and I increase L2. And we keep on doing this either till L1 is not null or L2 is not null. And if L1 is null, which means whatever there is left in L2 is P's next. So we'll attach the last element of the linked list, the sorted linked list which we are creating, to L2 in this case, because L1 is now null, and vice versa. If L2 is null, we attach P's next to L1, and then we return dummy nodes next. Yeah, So that was a quick iterative solution. So whichever you like is the one we can go with. So this question is quite similar to merge two sorted lists, but instead of two, now we have k sorted lists and we have to merge all of them to form a single linked list. And here they do not say that you have to merge the existing nodes, like interleave the existing nodes. You could potentially create a new linked list and just return the head of that new linked list if you like. So similar to previous case, we can do is we have k linked lists. So we'll find the linked list with the minimum smallest element, and then we'll add it to our overall sorted list, and then we again find the smallest element from this k list. We append that, we find the smallest, we append that, we keep on doing that and until we build the complete list. So the point is that to find the smallest element among the k linked list, it would take order k if we just do it like linearly. For every element in the final list, we have to do this order k operation of finding the smallest element from the k list. So time complexity of order n into k, where n is the total number of nodes in the final list which we have to return. So we can improve this a bit if we use something like min heap, which will at most store k elements, and those k elements would be the heads of these k linked lists, and every time we pop from that heap, what we can do is we can store along with the value in the heap the index of the linked list, basically which linked list does this value belong to, and then we can delete that node from that linked list, attach it to our main linked list, and then push the new value of the node from that linked list into the heap. And at every point of time, heap would have maximum of k elements, and finding the minimum is of order of log of k. So this will reduce our time complexity from order of capital N k to order of capital N log k, where capital N is the number of nodes in the final list. So this is a pretty good solution, but this one has a space complexity of order of capital N, since we would be creating a new linked list. If not, we can skip that, we can interleave the current elements if we want. So that's not necessary, but we will certainly have a space complexity of order of log k, where k is the number of linked lists. We need that space complexity for the heap. So that is one of the potential solutions, which is already very good solution. Another potential solution is to merge this k sorted list like a merge sort. So what we do, consider a base level where we have k sorted lists. So we take the first two sorted lists, we merge them. We take the next two sorted lists, we merge them. We take the next two sorted lists, we merge them. And we keep on doing until we have like all the k sorted lists merged in pair, and then we have a new level of these sorted lists, and then we again merge them, and then we have a new level of sorted lists, and again merge them, we have a new level of sorted lists, and again merge them until we have a single big sorted list. So we have maximum of log k levels because we have just k different lists, and every time we are picking two lists and merging them into one. So we have maximum of log k levels, and at every level the amount of operation in merging would take order of capital N time, because those are the number of nodes we are merging actually. So total number of nodes merged at any level is capital N. So overall time complexity would be order of capital N log of K. So time complexity is similar to the heap solution, but space complexity is better because in this case we do not need extra space. So we can quickly write this solution. So let's jump right in the code. So we need to simply write the first solution which we mentioned. First we have to write simply a function which merges two linked lists. So merge two lists, L1. So these are the two linked lists. So to merge them, we create a dummy node. We have a pointer. If L1's value is less than value, if L1 value is less than LT value, sorry, then P is next is equal to L1, P is equal to P's next, L1 is equal to L1's next, else same thing, P's next is L2, P is equal to P's next, and L2 is equal to L2's next. If L1 equals to null, P is next equal to L2, else P is next equals to L1, and we return dummy nodes next. So this is the merge to list function which we wrote earlier today, and now we have to merge these K lists. So what we can do is now we have a vector and each element in a vector is a pointer to one of the lists. So what we'll do is we'll merge the first element with the last element and store it in the first element. So we'll merge list 0 with last element is ln minus 1, list 1 with len minus 2. So this with this, this with this, this with this, and keep on going like that. We merge these two, store in this. We merge these two, store in this. We merge these two, store in this. And we keep on going like that. And after doing that, we update len is equal to len plus 1 by 2 plus 1 in case it is an odd number. So if like original length was 4, new length would be 5 by 2, which is 2. But if original length was 5, new length would be 5 plus 1 by 2, which is 3. Because first and fifth would be merged, second and fourth would be merged, third would not be merged with anyone else, because I would stop at 5 by 2, which is 2. So 0 and 1, I will only take value 0 and 1. When I becomes 3, this loops exists, so third element would not be merged. So ultimately the length would be 1 and it would be stored in the first most element of the list, so we can simply return list 0. So hopefully it works. Let's try. It's list. So this one was successful. Let's try to submit the code. Oh, time limit exceeded because we have an empty list. So if list dot size equals to 0, return null pointer. So let's try to pass the empty list. Yep. Yeah, so the code is accepted. Brief summary, we create the merge to list function which we wrote earlier. So this is the main part. If list size is 0, we return null pointer or corner case. Then we check the length of the list. What we do is we merge the first and the last list and store it in the first list. And we merge second and the second last list, we store it in the second list. We merge the third and the third last list, we store it in the third list. And when we have merged this, we assume that the length of the list has been decreased by 2, and then this is the new list we have. We keep on merging until the length of the list is decreased up to only just length is 1, which means now all the lists are merged, and then we return that. So we did not use any extra space. So this is order of capital and log k time and no extra space. So let's move to the final question of the day. This is a medium question. So there is an integer array num sorted in ascending order with distinct values. So this is important. Prior to being passed to your function, nums is rotated at an unknown pivot index k, such that the resulting array is nums k plus 1, nums n minus 1, last element, and then first element. For example, if this was the array 0, 1, 2, 4, 5, 6, 7, it's rotated such that it's now like 0, 1, 2, 4, 5, 6, 7. So basically it's pivoted at index 3. So starting from index 3, we started rotation from here. So we started from here 4, 5, 6, 7, and then rest of the elements 0, 1, 2. So given the array nums after the rotation and an integer target, return the index of the target if it is in the nums, or -1 if it is not in the nums. So we have to find this target in this array. So if this was a simple normal sorted array, we could use binary search, but this sorted array has been reversed. So what we can do is, like, even if it is reversed, this part and this part, like, you can think of it as two sorted arrays within one sorted array. So we can search in this sorted array in order of whatever the length of this is, and we can search in this sorted array separately. So searching this sorted array would be maximum order of log n, where n is the total number of elements in this array. Searching this sorted array would be maximum of order of log n. So it would be order of log n plus log n, 2 log n. And then the important thing is, how do we know that where does this sorted array start from? What's the separation between these two kinds of sorted array? And we have to find that pivot index, and we can find that pivot index using the binary search approach itself in order of log n. So it would take us order of 3 log n, 3 times order of log n, which is kind of order of log n, to solve this question. So let's see how we can find this pivot. So to find this pivot, imagine that array was like increasing array, and we kind of cut this array in the middle and we made it like this. So now there is an increasing array, and then there is a slight dip, and there is again an increasing array. So we have to find this dip when the next element is like this element is less than the previous element. So let's say if first we have to note that if nums 0, let's say size, total number of elements in array nums is n. So if first element is less than last element, which means the complete array is sorted and the rotation was not done, so it was 0 indexed. And in this case we simply return binary search nums with our given target. Simply return that. Otherwise we try to find the pivot. So how can we find the pivot? We can say int l is equal to 0, r is equal to n minus 1. We say mid is equal to l plus r by 2. And we say if nums mid is greater than nums of mid plus 1, if the middle element is greater than the next element, which means this is the pivot point. So we can say pivot is equal to mid pivot is equal to mid, and we can break here, else how do we know if we are in the first array or if we are in the second array? We can check that by using that if the value is less than the first element in the array, that means we are in the second half. Otherwise we are in the first half. So else if nums mid is greater than nums l, in fact nums 0, which means mid is in the first half. If mid is in the first half, we can increase our mid we can increase our L to be mid plus 1. Because mid is not the pivot, then no need to search. Like let's say mid standard here, so 6 is not the pivot, so no need to search here. Now we will search from here. So L is equal to mid plus 1. Else if it is in the second half here, so let's say mid was 0, which means L was 3, R was 6, 3 plus 6 is 9, by 2 is 4, and that's why mid was 4. So if mid was pointing to 0, which means we are in the second half, in that case we'd like to decrease our pointer to mid minus 1, and we keep on doing this while L is less than equal to R. So once we find the pivot, so let's say int pivot. In fact, we can just leave it to be mid, and here we can just add a break. So our mid is serving as the pivot. So in this case we'll return, so we'll binary search the target, int answer 1 is equal to binary search the target, in nums from 0 to mid, binary search nums from mid plus 1 to n minus 1, and if answer 1, if we found the element in the first half, we return answer 1. If we found the element in second half, we return answer 2. Otherwise we return minus 1. Now this would be binary search between 0 to n minus 1. So let's quickly implement this binary search function. This is our normal binary search. So while L less than equals to R, if int m is equal to L plus R by 2, if nums m equals to target, then we have found the index, we return m. Else if nums m is less than target, we L is equal to increase the L else we'd increase the R. And if we did not find the element, we return -1. So let's quickly try to run this code. I was not updating this mid, in fact. So yeah, so our mid was 3. So we found in 0 to mid. We found in mid +1 to n -1, and we got the correct answer. So let me remove this. Now let's try to submit our code. So if the element has only one input, I don't think we handle that case. If nums is less than nums n minus 1 or n equals to 1. In both cases, if there is just like one element, we got the wrong answer for this case. Let's quickly see what's happening. And after these, what would head L become? So nums mid is greater than num0. This is false. So R is equal to mid -1. So R becomes 0 in this case. I see. So I think we should keep it to be like that. Let's keep R to be always in the right half. So R will always point to the element in the right half. So this way R will always point to the right half. Yeah, code has been accepted. So for a quick summary, what we did was we find the pivot point. The way we did it was that we found the element mid such that nums mid is greater than nums mid +1, and if nums mid is not greater than nums mid +1, we check whether mid is in the first half or in the second half. If nums mid is greater than nums0, it's in first half, and we can increase L is equal to mid +1. Otherwise it's in second half, and we decrease shrink R to be equals to mid. And once we have identified two halves, we just run our normal binary search in those two halves and return the answer accordingly. So that covers our last question for today. I hope you like this video. If you like this video, share it with your friends. Subscribe to my YouTube channel. Click on the bell icon. Comment what did you like about the video. Comment any mistakes you found in the video. And thank you so much for watching this video. We'll see you in next video. Bye bye.